Hello there. In this video, we're going to introduce the topic of hypothesis testing, which corresponds to sections 10.1, 10.2, and 10.4 in our textbook. This particular video is going to introduce us to the preliminaries of hypothesis testing, while subsequent videos will focus more so on applications and examples. So a natural place to begin is to figure out what exactly is hypothesis testing, and quite frankly, why do we care about it? So let's consider this example. If the true proportion of all Wayne State students who applied elsewhere is p equals 0.35, what is the probability of getting a sample with p hat being greater than or equal to 0.375? Now, truth be told, we need one more piece of information in this particular question, which is the sample size, and we would actually be able to figure out what this probability is using some of the techniques from Chapter 7, namely our z-scores with the sampling distribution. But if we want to extend this a little bit more further and ask whether or not this particular sample is even possible, considering a certain parameter, p or mu, then we get into the notion of hypothesis testing. So hypothesis testing itself is a procedure that enables us to choose between two hypotheses when we're uncertain about our measurements, that is our statistics. So we try to have some kind of uniform standard for evaluating claims on the parameters. And you have to remember that statistics, at least on the inferential side, is all about trying to figure out what the population is like, what's it doing. And so because we don't know a lot about our population parameters, we have to make inferences, and we use the samples to help us, and the hypothesis testing is one way to help us with those inferential side of statistics. Now, hypothesis itself, very simply, is a theory or premise, and it's often a claim that someone is making that we have to investigate a little further. So there's some research that has to be done. Maybe there's an experiment, maybe there's a survey, whatever, in order to obtain and figure out the statistic and then move forward with testing our claim more formally. Now, the first steps to hypothesis testing actually begin with forming the hypothesis. So, how do we do this? Well, we have to establish what we call the null and the alternative hypotheses. So, every hypothesis test has two component hypotheses. One is the null, and the other is the alternative. Now, the hypotheses are always statements made about the parameter, and the variables used should reflect this. You'll notice this statement is bolded and underlined because it is important. It's there for emphasis. So because these are statements that are made only about parameters, the variables we use can only be p, which stands for the population proportion, or mu, which is the population mean. So remember those two variables, very, very important. So we're not using x bar and we're not using p hat in the hypotheses. Now we have something called the null hypothesis, and you see the notation there written as HO or H naught. The null hypothesis is known as the conservative or status quo statement that we make about a parameter. So the statement is often the no change, no effect, or no difference statement, and it always carries the equal sign with it. And so if we return to our example about the true proportion of Wayne State students who applied elsewhere, and we think that it's 0.35, and then we've got this sample statistic that it's reporting, the null hypothesis here would be very simply p is equal to 0.35. Now, alternatively, we have the second hypothesis, which is known as the alternative hypothesis, or HA. This is commonly referred to the research hypothesis. So this is the statement about the value of the parameter we hope to demonstrate is true, okay, given some sample statistic. So this is often the statement that we want to test the claim of. Okay, this is the one we are interested in. Okay. Now we have two forms for the alternative hypothesis. The first form is known as the one-sided or one tail. And the reason it's called one tail is because either we're dealing with area on the right or we're dealing with area on the left. Now, if you look at the null hypotheses on the one-sided test, you'll notice that the equal sign is always in the null. Okay, we talked about this. You'll notice that the two differences, or the one difference that we have is in the alternative, where the alternative in the first example is greater than, and in the other one it is less than. So the greater than is area to the right, less than is area to the left. Okay, so those are the forms for the one-sided. For the two-sided, it's actually rather simple. The alternative just carries the not equal to. Okay, and the null again is the equals. So again, note that both the null and the alternative hypothesis are statements made about the parameter. And at least in the context of what I'm demonstrating here, I'm using p. I could have interchanged this very easily with mu. Okay, we just can again use p hat or x bar. Now, the textbook uses what we call the equality convention. And what this means is that the null hypothesis always has the equal sign. So it's just p equals 0.35. Okay, and then the alternative fits one of the other forms that we've talked about. There are some textbooks that use what's called the complement convention. And so what they do is they take the complement of the alternative hypothesis. So for example, if the alternative is greater than, then the null hypothesis would be less than or equal to. Similarly, if the alternative was less than, then the null would be greater than or equal to. And so I'm showing you this because if you take future statistics courses, they might actually use the complement convention, while others will simply use equals for the null hypothesis. Regardless, the main takeaway here is that the equal sign is always with the null, whether it's written as a less than or equal to, or greater than or equal to, or just equal to. Now let's get into some examples of hypothesis tests and actually putting the hypotheses together. So I'm going to walk through the first one with you, and there are two other examples that I would encourage you to pause the video and try on your own. So what I would encourage you to do now is pause the video and give this problem a read over, and then we'll talk about it. Okay, hopefully you've had an opportunity to read this problem. The first step that I usually do in thinking about these problems is asking myself, is this dealing with means or proportions? And if you read this carefully, you're going to notice that we're not talking about any kind of proportions or fractions or decimals or percentages in this particular case. It's just very simply 10 hours per week. That's considered a rate or an average. So the variable that I'm using in my null and alternative is going to be mu. Now, the value in question here is 10. Okay, so the null hypothesis here is very simply going to be mu is equal to 10. Now, the question is, what is the alternative? So remember, the alternative hypothesis is the hypothesis that we're interested in learning about. We want to understand more. So if you look at the last sentence here, this director is curious to see if students are being required to spend more than 10 hours per week doing work. Therefore, the alternative is going to be that average, that mu, is greater than 10 because that's what they want to test. And those are the two hypotheses for this particular hypothesis test. Now, for this example, what I would encourage you to do is pause the video, read the problem, and you try and put the hypotheses together. Okay, hopefully you've had a moment to do that and get the hypotheses. So first things first is decide on the context. And so if you read this one carefully, you would have noticed that there's no, again, percentages or decimals. And the word mean is floating here. So this suggests to us that we are using mu. So this is all about means in this particular problem. Now, the only value that we're looking at here in question is 30 seconds, okay? So first of all, the null hypothesis would be mu is equal to 30. Now, the question is, what is the alternative? Well, if you read the second to last sentence in this scenario, there's evidence here that says that the mean time is different if the water temperature is colder. And reading further, it says the group wants to test that claim, that it's different than 30. So what does different mean? Well, it means it could be more. It means it could be less. So how do you write that? Well, we say that it's not equal to 30. And so that helps us to see then that it could be more or it could be less. And our last example, feel free to pause the video and give this one a shot. Okay, hopefully you've had an opportunity to write out the hypotheses here. The first thing to notice is that we have 56%, and the word average and mean is absent in this problem. So this particular case, we are dealing with proportion. So the variable you're using in both hypotheses, the null and alternative, is p. So the null here is going to be p is equal to 0.56, since that's what 56% is as a decimal. Now the question is, what is the alternative? Okay, well, if you read the first sentence, it says the news agency claims or thinks that the rating has dropped in the past 3 months, and the chief of staff wants to test that claim. This means that they want to test that p is less than 0.56. So this is often the first step in a hypothesis test, is building the hypotheses. And so this would be the steps that you would go through in order to do that. What we're going to spend a moment talking about now are the next set of steps in the hypothesis test, and it deals with something called a significance level. And so what we do after we have the hypothesis test established is we compute what's known as the p-value. Now you'll notice that this is highlighted in yellow. This is where you would fill in the blanks on the guided notes that are provided. So what is a p-value? Well, simply a p-value is a probability that we get a statistic that is as extreme as the one we found in our sample. Now, we use something called a test statistic to make a decision about the null hypothesis, and we derive the test statistic from the sample statistic. Okay, that's a mouthful. What is this saying? Very simply put, the test statistic is a z-score. That's it. Okay, that's your main takeaway here. What is a test statistic? It's a fancy name for a z-score. So how to get a z-score? Well, we're going to use some stuff from chapter 7. How do I know that? Well, it's depending if we're using means or if we're using proportions. Okay, so we do the computation, we get our test statistic, our z-score, then we go look it up. Okay, we go to the normal table, we look it up. That value we get off the normal table, that probability, that's your p-value. So that's how this works. Pretty simple. Now, the sample statistic said to be statistically significant if it's far enough away from the presumed value of the population parameter to conclude that it would be unlikely for the sample statistic to occur by chance if the null hypothesis is true. Okay, what is this saying? What this is saying is my sample that I found, is it rare enough? That's the question here. If it is, we call it statistically significant. Now, what do I mean by rare enough? Its p-value, its probability is small. It's in the tails. That's what we mean by far enough away. Okay, so if you remember, if you're way out in the tails on the normal distribution, that area is very, very small, considering if you're looking to the right or the left, depending on which direction you're at. Finally, we have something called a level of significance, which is denoted by alpha. This is the probability of making the error of rejecting a true null hypothesis in a hypothesis test, and alpha is equal to 1 minus c. Now, we'll talk about errors in the next video, but it is possible that we could make an error not by our own computation. It's just possible. There is some likelihood here. So hypothesis tests are not for certain. There is a little bit of risk involved. So if the p-value of a test statistic is less than alpha, then we say the test is significant at this alpha level. Okay, and so what it does is it lets us know whether or not the data is in favor of one of the hypotheses. And alpha is always a level we decide on. If you're looking to do research, you actually pick your alpha before you do the experiment. Very, very important that you pick that alpha value. And this will make sense when we look at some contexts. Now, what we do is we compare the p-value to this alpha level, the statistic, and then we have to make a decision. And so the decision has two forms. The first decision form is we reject the null, and the other one is fail to reject. Now, some people might say, well, why don't you just say accept the alternative instead of failing to reject the null hypothesis? And that's a worthy question. This is just the convention that we use. Remember, we're not proving anything about the alternative hypothesis. Hypothesis tests don't prove anything, so we have to be careful here. So if the p-value is found to be statistically significant, which again means it's less than alpha, then we reject the null hypothesis in favor of the alternative. So this is what we want to happen. We're happy when this happens because that means our claim was potentially true. Now, if it was found the other way around, where it's not statistically significant, which means that our p-value would be more than alpha, then we fail to reject the null hypothesis. So again, we assume the null hypothesis is true unless we find statistically significant evidence to the contrary. And then the final step is to actually draw a conclusion in the context of the claim. So this essentially means that we answer the question. And so usually the question is there enough evidence to suggest that? And then you fill in the blank with whatever the context is. So this concludes the preliminary information on hypothesis testing. And what we'll look at next gets into some error types as well as the first example of a fully worked test.